Hi, I'm Shudeshna. I'm going to talk about near-field scanning optical microscopy, in short, NSOM. But before I start over, I'll just like to put a little disclaimer here that my drawing is bad, really bad. So please bear with me for the next couple of minutes. Alright, let's get started. Remember your biology classes where you used to put glass slides under the microscope to see teeny tiny organisms? And we used to be pretty excited to keep on magnifying. And then after a certain point, we would realize that no matter how much you magnify, all you see is blur. So what could be the reason for that? The reason is diffraction limit. So what is diffraction limit? At this point, I would assume that you all are aware of the phenomenon diffraction. We know that light travels in waves. So even if it appears that an optical lens focuses a light beam to a point, if we look close enough, it's not exactly a point, but a fairly spread out spot. Ernst Abbe in 1873 first described this phenomena as diffraction limit of light, and the diameter of that spot given by him was d is equal to lambda by 2Na, where lambda is the wavelength of the incident light and Na is the numerical aperture. So for visible light, the diffraction limit comes out to be 200 nanometer, and this 200 nanometer zone is termed as airy disk. So what happens is that lens cannot focus a light to a point smaller than 200 nanometer, and everything inside this 200 nanometer zone becomes indiscernible from each other. Just like the two teeny tiny cells over here. Just see, they are feeling sad because they are not being discernible. Thus, the resolution of conventional light microscope gets limited. The solution? Let's beat the diffraction limit of light. But how? For diffraction, light propagates through space in an unconfined manner. So, what if we can generate confinement on its way of propagation? Can we beat the diffraction limit by that? Let's see. How do we generate confinement? Confinement is usually generated by using aperture. An aperture is a tiny hole on an opaque screen having dimension much smaller than the wavelength of light, usually in the order of 50 to hundreds of nanometer. So this is an opaque screen. When light passes through it, it gets confined. This confined region is called near field and the rest is called far field. The near field or evanescent field exists at distances less than a single wavelength of light from the surface, around tens of nanometer. Here the light is collimated, but it decays exponentially. So you can think of a liquid gushing out of a very fine orifice that comes out pretty straight near the hole and that spreads out away from the hole. So the idea is to place our sample in the near field way before the diffraction limit is imposed by the far field. No diffraction, no diffraction limit. This idea was first conceived by Singe in the early 20th century. Basically, the concept is that resolution becomes dependent on aperture and not the wavelength. So we fine-tune the aperture to enhance the resolution. With the finest designing of aperture, resolution down to 50 nanometer has been achieved. From the discussion before, we can conclude that two most important things to control in NSOM are aperture and positioning of sample. Aperture is the heart of any NSOM setup. Normally, fiber optic probes coated with reflective metal are used. Uncoated sharp tips are also used. But these probes are subjected to issues like artifact, distortion of sample surfaces, etc. Apertureless probes are a solution to these issues where the end of a sharpened metal tip is illuminated, creating an oscillating surface. The concept of photon tunneling microscopy through sharp tips are utilized here. The second crucial thing is precise positioning of sample, which is accomplished by a feedback mechanism. The feedback mechanisms commonly used in NSOM are of two types: shear force and constant force. Constant force feedback utilizes modes which are similar to that used in atomic force microscopy, that is AFM. For example, contact mode, where the tip directly touches the sample surface and maps the topography of the surface. In non-contact mode, the tip doesn't touch the sample. Instead, a high-frequency generator oscillates the tip through a piezo stage and takes measurement utilizing the long-range forces acting between the tip and the sample. The third mode is tapping mode. Here the tip is flexible. It deflects according to the topography of the sample as it moves over the sample, and the angle of deflection is measured by a laser coupled with a position sensitive detector or PSD. In shear force feedback mechanism, mechanical vibration is introduced to the tip by using a tuning fork. So here's the tuning fork and here's the fiber optic probe attached to it. The tip vibrates laterally at resonance frequency less than 10 nanometer. The sample is placed just beneath the tip. Now as the tip approaches the surface, the amplitude of vibration gets dampened, as you can see from here. And now by monitoring the dampening of amplitude of vibration of the tip, a feedback signal is generated and thus the tip sample distance is controlled. So this is what an NSOM setup would look like. Laser light is coming through the fiber optic tip. Closer to the tip, the sample is placed over an XYZ piezo stage. Both the piezo stage and the tip is connected to a feedback control unit. Beneath the sample, there is collection optics and an avalanche photodetector or APD. The detector is usually connected to a spectrograph and a computer. Depending on the mode of feedback control unit, a laser PSD pair is also mounted. Now let's talk about the applications of NSOM. The most investigated applications of NSOM are in bioimaging and thin film analysis. I've got few images to show you. This is an image of a muscle tissue and this is an image of amyloid fibril. Also for thin film analysis, this is the images of bilayer, polymer bilayer, and this is an image of thin film of PPEI crystal. NSOM is also being applied in single molecule fluorescence imaging. One of the limitations of NSOM is that it is kind of limited to study surface phenomena only. But this field is developing, so we have hope. Alright, so this is my small presentation on NSOM. I'll leave the references in the description box, so go ahead and check them if you are interested enough. Thank you for watching. Hope you like it.